Hey everyone, welcome back to the College Algebra playlist. In the previous videos, we took a look at linear equations. Alright, this chapter in the textbook is all about solving equations and solving inequalities. So for future videos, we're going to look at quadratic, rational, and radical equations. Alright, but before we do that, we need to make a small detour and talk about complex numbers. Alright, we need to talk about these because sometimes the solutions to quadratic equations are complex. All right? So let's gain our foundations with complex numbers right now. Okay, here we go. Introduction to complex numbers. Let's talk about some subsets of the real numbers first. All right, numbers that fill a void. Negative integers fill a void left by the set of positive integers. All right, for a long time, people didn't think that negative numbers existed, but we need them in math, right? Also, rational numbers, right, which are fractions, fill a void left by the set of integers. All right? Real numbers fill a void left by the set of rational numbers, okay? Because real numbers include irrational numbers like the square root of 2. All right, they can't be written as a fraction. And finally, it's not surprising that complex numbers fill a void left by the set of real numbers. Okay? So what are these voids that are being filled? Let's talk about that. Negative integers, right? We need numbers less than 0. Okay? And rational numbers, right? Fractions, we need numbers for division. All right? And with real numbers, we need numbers like the square root of 2 that aren't fractions. All right, we need the square root of 2, for example, if we're solving for the length of the hypotenuse of a triangle with side lengths 1. Okay, so that's irrational. And for complex numbers, we need solutions to equations like x squared plus 1 equals 0. All right, so let's take a closer look at this equation. All right, and let's solve it. This is our first quadratic equation in the video. All right, this is just a sneak preview of what we're going to see in a future video, right? We'll talk about quadratic equations a lot more later, all right? But basically this power of 2 on the x makes it quadratic, okay? So to isolate x, what we need to do first is subtract 1 from both sides, okay? So we do that, and then we get x squared equals negative 1. All right? This is impossible. Okay, you can't square something and get a negative number. All right, it's not possible. Take this for an example. 5 squared equals 25. Okay? And if we square a negative number, right, we also get a positive result. Negative 5 squared is 25. Okay? So this equation, right, we can't do it with real numbers, all right? But let's try to isolate x anyway and see what we get. All right, let's just roll with it. The square root and the square, right, they undo each other, and on the left-hand side, we're just left with x. Okay, so that gives us x equals the square root of negative 1. All right, that's not a real number. Okay, so there's no real solution to this equation. All right? So if we wanted to, right, we would say there's no real solution, right? Pack up our bags and call it a day. All right. So this is true that there's no real solution. But what if instead, what if I take this square root of negative 1 and just give it a name? All right, let's just call it I. Okay. We're going to treat this as a valid number. All right. If it's not real, right, that could mean it's not valid, but we'll just try naming this thing I, right, and take it and run with it. All right, so instead I'm going to say my solution is x equals I, and that's my imaginary solution. All right, this is an imaginary number. The imaginary number I is defined as I equals the square root of negative 1. Okay? And check this out. If we square both sides of this equation, we get I squared equals this, right? And the square root and the square undo each other, and on the right-hand side, we're just left with negative 1. Okay, so I squared equals negative 1. All right? So this is what an imaginary number is. And we can write the square root of any negative number as a multiple of I. Take, for example, the square root of negative 49. All right, I'm going to rewrite that as the square root of 49 times negative 1 under the square root. All right? And then I'm going to split that into two radicals. Okay, why can I do that? All right, why is this valid? It's because of an exponent rule from earlier in this playlist. All right, if I have a product to some power, I can take that power and apply it to each piece of the product. Okay, a square root is the same thing as an exponent 1/2. All right, so I'm taking this product and I'm applying the 1/2 power to each piece of the product. All right. So we're going to be doing this a lot in this playlist, so it's important to get comfortable with it. All right, we split this radical up into two. All right, and the square root of 49, that's 7. And then this square root of negative 1, right, we've given that a name, it's I. So we have 7I for our solution. 7I is an imaginary number. All right, a complex number is the sum of a real number and an imaginary number. A complex number is expressed in standard form when written as a plus bi, where a is the real part and b is the imaginary part. All right, here are two examples of complex numbers, 5 plus 2i and 3 plus 4 root 3i. Okay, so this 5 in blue here, that's the real part, and the 2 in red, that's the imaginary part. Okay, so a complex number is defined by two numbers. All right, that's going to be important later. For now, though, let's just stop and ask ourselves, why are we doing this? All right, why does this matter? Why do complex numbers matter? Well, this is a short list of real-world applications of complex numbers, okay, where imaginary numbers are being used. Electrical engineering, signal processing, quantum mechanics, fluid dynamics, and electromagnetism. All right, so complex numbers are everywhere. All right, there's a whole branch of math. All right, there's a whole class called complex analysis. All right, I highly recommend you take that class, by the way. It's really interesting. So we've opened up a whole new world of math just by acknowledging that I equals the square root of negative 1 is a valid number. Okay? Let's go back to standard form, right? Here we're asked to write 3 plus the square root of negative 24 in standard form. All right, so we should have something plus something I. All right? So I have this, and once again, under the square root, I'm going to write this as a product, okay? I'm going to write it as the square root of 24 times negative 1, okay? And 24 is 4 times 6, all right? 4 is a perfect square hiding in here, all right? So that's going to help us out when we're trying to simplify this. All right, so once again, I'm going to break this radical up, all right, this time into 3 radicals, okay? So I'm taking the 1/2 power and I'm applying it to each piece of the product, all right? Look at what we have here. The square root of 4 is just 2. And square root of 6, that can't be simplified any further. And then finally, I have this square root of negative 1 at the end, right? So it's 3 plus 2 root 6 times I. All right, that's our answer. Something plus something I. That's standard form. All right. Let's take a look at those voids that we were talking about earlier. All right. How do certain numbers fill certain voids left by other numbers? All right. These are the positive integers, right? And we can see that this picture is incomplete, right? There's a void here. What we're missing is the negative numbers. All right. The negative integers show up here and we get a more complete number line. All right. Also, we can identify rational numbers on this number line. All right. So these numbers are here too. All right. We're getting a more complete picture. Also, irrational numbers, like the square root of 2, show up on this number line. All right. So we're filling this out nicely, right? We're filling it out with some numbers. Okay. Let's call this axis here, let's call this number line the real part, okay? So we'll label it with RE, all right? complex numbers are defined by two numbers. All right, so those are sort of like coordinates in an ordered pair, right? So what we're going to do is extend this number line by adding a vertical axis. All right, this is the imaginary axis. Okay? Let's zoom out and take a look at what we have now. All right, this is the complex plane, where this horizontal axis is the real part and the vertical axis is the imaginary part. Okay? We can visualize complex numbers by plotting them on this complex plane. All right? For example, 3 plus 2i, right? We go 3 in the real direction and we go up 2 in the imaginary direction, right? And we get 3 plus 2i. That's where we locate our complex number. All right? And here in blue, right, I go to the left by 2 because it's negative 2. And I go up by 4 because it's plus 4i. All right? So there's my blue point. Down here, I go to the left, negative 5, and I go down negative 4 to get to negative 5 minus 4i. Okay, that's our red point. And then here, I go to the right by 4, and I go down by 2. That gives me 4 minus 2i. All right, that's where my green point is. Okay? So this is how we can visualize complex numbers. All right? Just as with real numbers, we can perform arithmetic operations on complex numbers. All right? To add or subtract complex numbers, combine the real parts, then combine the imaginary parts. All right? So if I have one complex number plus another complex number, what I do is I group together the real parts, right? A plus C, and then I group together the imaginary parts, right? BI plus DI, and then we can factor out that I to the right. Okay? So that's sort of like a reverse distributive property there. Okay, that's addition. And subtraction, we do the same thing, but we just make sure we're careful with how we distribute this minus sign to each piece. All right, we group together the real parts, right? That's A minus C. And group together the imaginary parts, right? That's B minus D. Okay, so that's subtraction. Let's try this out on a concrete example. Here we're asked to add the complex numbers 3 minus 4i plus 2 plus 5i. All right, the first thing I'm going to do is get rid of the unnecessary parentheses. All right, then I'm going to group together the real parts, right? 3 and 2. And then group together the imaginary parts, right? Negative 4i plus 5i. Okay? So I factor out this I to the right. Okay? And then I say 3 plus 2 is 5, right? And negative 4 plus 5 is 1, right? So I just get I. So I have 5 plus I. All right? Notice that negative 4i plus 5i, it's sort of like we're adding like terms here. Right? That's what it's reminding us of. All right? So we add the like terms and we get 1i. So we just get I. All right? That's addition. So this is my final answer. All right? Let's try subtraction now. All right? Here we're asked to subtract negative 5 plus 7i minus negative 11 plus 2i. Okay? So when we get rid of the parentheses here, right, we need to distribute this minus sign to each piece in here. All right? That gives us negative 5 plus 7i plus 11, right? Minus negative 11 is plus 11. And then we get minus 2i. Okay? So the parentheses are gone, so we can rearrange this thing to get what we want in standard form. All right? Factor out this I on the right again. We have 7 minus 2i. Okay? In parentheses over here, negative 5 plus 11, right? That's 6. And then 7 minus 2, right? That's 5. Okay, so we get 6 plus 5i. And that's our final answer. That does it for this video. Thank you for watching, and like and subscribe.